Hi, we are the UCF ASHRAE Design Competition Team, and I'm Mehboob Sayed, one of the drafters on the team. Our project is based on the 2026 ASHRAE Design Competition, specifically the Setty Family Foundation Net Zero Energy Design. The goal is to design a 93,000 square foot sustainable educational facility in Denver, Colorado that approaches net zero while meeting ASHRAE standards. To achieve this, we focused on maintaining occupant thermal comfort, ensuring long-term reliability, and selecting systems that are efficient, cost-effective, and easy to maintain. We also aim to create a healthy indoor environment while integrating renewable energy sources supported by load analysis and energy modeling. The main objective is to design a net zero HVAC system, meaning we minimize energy use while still meeting comfort, ventilation, and performance standards, long-term performance, and sustainability. Climate, this requires careful system selection to ensure long-term performance and sustainability.
There are several possible broader impacts of this project besides the building itself. First, the environment and sustainability. Because the main goal of the project is to achieve net zero energy, this project directly relates to creating a more sustainable and environmentally friendly future. Second, economic impact. Due to the high energy efficiency of the design, there'll be less energy costs over the building's lifetime, but higher initial costs compared to a non net zero energy design. There's also the possibility of the building contributing energy to the grid when it produces more energy than what it needs. Third, ethical. An engineer's ethical obligation includes maintaining and improving the welfare of humans. Net zero energy designs are sustainable and benefit the environment, thus allowing current resources to be available for future generations, directly improving the overall welfare of society. Health and safety. Due to this project utilizing renewable energy sources, the building design reduces the possible negative health and safety effects caused by pollution produced from typical fossil fuel energy plants. Socially, the building can have a lot of impact. The team is designing a university building, therefore, it will provide local communities with a facility for educational development, social development, and academic collaboration, all contributing to local social growth. Lastly, political impacts. All the above topics are related to modern politics to varying degrees. Therefore, the project is quite intertwined with politics.
We use different systems throughout the building. In the kitchen, we use the dedicated outdoor air system, or DOAS, in order to precondition the high outdoor air load. Makeup air units were used to balance the kitchen's air pressure from the hoods exhausting the air. And an air handling unit, or AHU, was used for thermal comfort. AHUs were also used in other zones to provide conditioned air into them. Bipolarization was used to reduce the amount of outdoor air needed in different zones following ASHRAE 62.1 IAQ method. This leads to less energy being used to condition the outdoor air. Variable air volume boxes, or VAVs, with electric reheat were used alongside the thermostat to provide thermal comfort into each room. 100% outdoor air handling units were used in zones that have air being exhausted because we do not want to recirculate the air in these zones, such as the metal workshop or research labs. Exhaust fans are used to remove the unwanted air from the building. For example, in restrooms, we are using exhaust fans to remove moisture and odors from the building.
To organize our information, we performed a takeoff. We gathered our data from the owner requirements and from the drawings provided, putting our information in an Excel sheet. In here, we have rooms organized by zone and marked each room's room name, type, measurement, number of people, fixtures, minimum number of exhaust air, outdoor air, as well as exterior window dimensions and orientation. Our values for exhaust air, outdoor air, and number of people were taken from ASHRAE 62.1 standard, which provided the necessary formulas for each. The data we collected in our takeoff was what we used in our hourly analysis program, aka HAP, to calculate building load and energy. Here in Bluebeam, you can see how we divided our building into zone types. As mentioned, we accounted for room types in each zone as well as solar radiation that would be hitting the building at different parts of the day. Since Denver, Colorado is located more north, the south side experiences more solar radiation. Therefore, we wanted zones located on the south part of the building to account for extra load. Throughout this project, we received help from a variety of professionals. We reached out to Dankin, Stanweaver, and Train, sending our equipment schedules and in turn receiving advice, equipment cut sheets, and Revit families for our project. Matern and Peninsula were able to provide us with better insight on the mechanical engineer's process on these kind of projects, help us with understanding net zero energy techniques seen throughout the industry, and help check over our thought process and provide us with any additional support we needed.
For this project, we approached net zero design the same way a real engineering firm would, by combining energy modeling, system performances, and a full lifecycle financial analysis, all within an $8 million project budget. We begin by modeling 3 HVAC configuration and carry HAP, air-cooled, water-cooled, and geothermal assisted. HAP provided complete annual operating costs, and the water-cooled system came in about $163,000 per year compared to the $137,000 for the air-cooled option. So from an annual cost standpoint, water-cooled is more expensive, and we acknowledge that. But annual cost alone doesn't drive engineering decisions. We develop a 50-year life cycle cost analysis for all major equipment. Over that period, AHUs totally roughly about $1.1 million in maintenance, chillers about $3.89 million, and pumps around $889,000. When combined with an initial and replacement cost, the HVAC system represents about $1.46 million in today's dollars. From a financial perspective, this matters because the water-cooled system delivers lower long-term energy intensity, which directly reduces the size and cost of the renewable system required to reach net zero. HAP shows the water-cooled system uses about 541,000 kilowatts of HVAC electricity, and the entire building totals about 810,000 kilowatts per year. That becomes our renewable target. We then size a hybrid solar and wind system to offset that load. Solar provides the majority of annual production, while wind stabilizes performances during nights and winters. Over the building's life, the avoided utility cost improves ROI, showing payback, and keep the net present value positive, even if the water-cooled system tightens the upfront budget. By integrating energy modeling, lifecycle analysis, and renewable system sizing, we created a solution that is technically sound, financially defensible, and achievable within an $8 million project budget.
Focused more on developing the building model in Revit, especially working with walls, layouts, and defining enclosed spaces so the geometry could be used for analysis. One of the main steps was organizing the model to support our mechanical design process. We carefully defined walls, spaces, and room geometry, which are essential for performance analysis and HVAC modeling. A key part of the model could be used beyond drafting. We prepared it so spaces could be identified and transferred into energy analysis workflows, supporting our net zero design goal. We prepared the model for export into train trace, allowing us to study building loads, zones, and system behavior more accurately.
Autodesk Revit was used to design the duct throughout the building. Static pressure and airspeed in feet per minute were considered. Size reductions were made following a diffuser to maintain these values. Duct sizing is very important because it ensures that air is flowing smoothly, which leads to energy savings. Return air is sized to maintain the pressurization in these rooms, and rooms with similar loads share a VAV box. The thermostat is then placed in the room with the highest load to control the air.
To understand the calculations completed by HAP to obtain the desired energy calculations for all rooms in the building, the team has decided to perform a mathematical modeling of one room individually by hand. Office 2227 is a 104 feet squared room, and the desired set point temperature is 75 Fahrenheit. All calculations will be compared with the HAP output report. We begin by accounting for all the heat being added inside the office. Here, the envelope is not exposed to the surroundings, meaning the windows, walls, roof, and door are not adding heat into the office. Next, the lighting loads depend on the area and the office type obtained from property tables. There's one person in the office. People add sensible heat through emissions by the body and latent through sweat. We group the equipment loads in the miscellaneous section, and we've chosen which equipment will operate in the office. The factor of safety helps account for the negligible heat that fenestration adds, and the total space loads add up to 1812 butane per hour. There are two values of interest for the project that help the team pick which HVAC systems to install. The total system loads tell us how much heat the system needs to remove, which includes the heat added by the space calculated already, heat being added from outside the air using harder calculations included here, and the heat added by the supply fan, converted to butane per hour, and the system loads are 2468 butane per hour. The zone conditioning shows how much is being added by the central coil, which requires heat equation. We use the density of air at our altitude and the heat capacity of air and a specific form that helps us proceed. We use the temperature of air going inside and outside the space. We use the thermostat temperature as an initial guess, and the heat in the space was 2080 butane per hour. The values converge to 97 cubic feet per minute and 78.4 Fahrenheit. Then another loop is done with an initial guess near the saturation line and a psychometric chart. The final values converge to 50.5 Fahrenheit and 2397 butane per hour. These two load results help the team create the schedule and move on with the HVAC installation choices. Our team feels confident that we will perform well in our submission to ASHRAE on May 4th. This project demonstrated that it is possible to design an energy and cost-efficient building HVAC systems while meeting all thermal comfort and descriptions set by the stakeholders. Beyond the explained analysis, our team plans on providing ASHRAE with realistic calculations to further provide power through solar panels and wind turbines, as well as other suggestions the stakeholders could use to improve the overall comfort and safety levels. Additionally, our team will continue to verify our results from HAB by simulating the building performance on trains and perform more comparisons. Thank you for listening to our video description submission.